All right, let's jump right into a really cool computer science puzzle. Think of it like trying to find the longest possible uphill path through a whole mess of numbers. This thing is called the longest increasing subsequence.
So, let's kick this off with a simple rule, but one that basically unlocks the entire problem. Just imagine you're hawking through a list of numbers. You can skip any of them you want, but here's the one catch. You can never, ever go backward. Your only job? Keep climbing up for as long as you possibly can.
And this little challenge has a name, the longest increasing subsequence, or LIS for short. And trust me, it's a fantastic puzzle because it shows how just one clever change in how you look at a problem can lead to a way better solution. Okay, so what's the official goal here? It's actually pretty straightforward. You get a big ol' list of numbers, right? And your job is to create a new sequence by picking numbers out of that original list. But there are two big rules. First, every number you pick has to be bigger than the one you picked before it. And second, you have to keep them in the same order they appeared in the first place. That's it. We don't even care what the sequence is, we just want to find its length. And right here is the absolute key difference we have to get our heads around. A subarray has to be a continuous chunk, no gaps allowed. But a subsequence, that's where the fun is. You can skip elements all you want, as long as you maintain that original order. And it's this freedom to skip that makes the LIS problem so interesting to solve. Here's a really great way to picture what's happening. As you're moving through the array, imagine each number has to make a choice. It looks back and asks, hey, is there an uphill climb that's already started that I can join? Is there someone smaller than me that I can stand on the shoulders of? Or it can just decide, you know what? I'm starting my own climb right here, from scratch. Now, your first instinct might be, hey, why don't I just try every single possible subsequence? And, well, that's a natural first thought, but it's a total dead end. Think about it. For every single number, you have two choices, right? Include it or don't. This means the number of combinations just explodes exponentially. We're talking O of 2 to the n. For even a kind of small array, this approach becomes impossibly, ridiculously slow. Okay, so we definitely need a smarter way to do this. So let's check out a much more methodical approach using a really powerful technique called dynamic programming. Instead of trying everything all at once, we're going to build our answer piece by piece. The absolute core idea here is to make a new array, we'll just call it DP, and it's going to store our answers as we go. But the value at DP of I isn't the final answer. Nope, it's something super specific. It's the length of the longest increasing subsequence that ends with the number at that exact spot, index I, in our original array. So, how do we actually fill up this DP array? Well, for each number, we're going to look back at everything that came before it. We're on the hunt for a smaller number that we can tack ourselves onto the end of. We find the one that already has the longest subsequence, and we just add 1 to its length. That becomes our new length. Let's see how that actually plays out. All right, let's walk through this example together. We start with 3. It's the first number, so its DP value is just 1. Easy enough. Next up is 10. It looks back, sees the 3. Hey, 10 is bigger than 3, so it can extend that sequence. Its length was 1, so our new length is 1 plus 1, which is 2. Okay, now things get interesting with the number 2. It looks back, and there's nothing smaller. So what does it do? It has to start its own little sequence all by itself, length 1. Same thing happens with the number 1. And finally, we get to 20. It looks back at everyone, and it can stand on the shoulders of 3, 10, 2, or 1. Which one gives it the best boost? Well, the sequence ending at 10 has the longest length so far, a length of 2. So 20 latches on, and its DP value becomes 2 plus 1, which is 3. So the biggest value we see in our DP array is 3, and that, my friends, is our answer. This approach is great. It really is. It's logical, it's methodical, you always get the right answer. But because for every single element, we have to look back at all the previous ones, we end up with nested loops. And that gives it a time complexity of O of n squared. It's good, for sure, but believe it or not, we can do even better. Okay, now we're getting to the real breakthrough. This is where a subtle but powerful shift in thinking completely changes the game and unlocks a much, much faster algorithm. This right here is the key insight. What if we just stopped worrying about what the sequences actually are? What if we only focus on what we absolutely need to build future sequences? If the only thing we need in the end is the length, we can throw away a ton of information and just focus on what matters most.
And this insight leads to an incredibly elegant solution. It combines a greedy approach, making the best possible choice at each step to keep your options open, with the lightning speed of a binary search.
So here's the new strategy. We're going to keep a special little list. Now, listen closely, because this is the tricky part. This list does not represent an actual subsequence. I repeat, it's not the answer itself. Instead, think of it like this. The item at index k in our list is the smallest possible last number we've seen for any increasing sequence that has a length of k plus 1. I know, it's a mouthful. But when a new number comes in, if it's bigger than everything in our list, great, we just tack it on the end. We've just made our longest sequence longer. But if it's smaller, we find the smallest number in the list that's bigger than it, and we replace it. This doesn't change our list's length, but it gives us a much better, smaller ending for a future sequence.
Okay, let's see this in action. Our list starts with just 10. Then 9 shows up. It's smaller, so it kicks 10 out. Our list is now 9. Then 2 shows up, it kicks 9 out. The list is 2. See the pattern? Then along comes 5. Finally something bigger. We just add it to the end. Our list is now 2, 5, which means we found a sequence of length 2. But here's the mind-bending part. Now 3 arrives. It's not bigger than everything, so what does it do? It finds its spot. It replaces the 5. Our list becomes 2, 3. Why on earth would we do that? Because a length 2 sequence that ends in 3 is way more promising for the future than one that ends in 5. It leaves the door open for more numbers. This process just keeps going, always priming our list for the best possible future.
So after we've gone through every single number, we're left with the list 2, 3, 7, 18. And here's the magic trick. The size of this final list, that's our answer. It has 4 elements, so the length of the longest increasing sequence is 4. Simple as that.
So there you have it, 2 very different, really clever ways to solve the exact same problem. Let's just put them side by side so we can really see the whole picture. The dynamic programming way is usually easier to wrap your head around at first. It's foundational, it builds the solution brick by brick. But the binary search method, that's the real star of the show. By using binary search to find the perfect spot to insert or replace, it gets us down to a significantly faster O of n log n time. It's just smart, efficient, and honestly pretty awesome. When it comes down to it, the list problem teaches a really powerful lesson that goes way beyond just coding. It shows us that true optimization isn't always about the path you're on right now. It's about making those small, smart choices that open up the best possible paths for the future. So the next time you're facing some complex problem that just has way too many possibilities, try to remember to ask yourself, what is the absolute essential piece of information I need to keep? And is there a shift in perspective, a different way of looking at it that I'm missing? Because finding that one little insight can be the difference between a good solution and a truly brilliant one.